Well, hello again, class. Time for us to move on to section 14.3, or unit 14.3, I should say, talking about increasing and decreasing parts of a function. So what does that mean? Well, a function is said to be increasing on an interval, and this means for x's only. We don't really care about the y's so much. When we talk about intervals, we're specifically talking about x's. So a function is increasing on an interval when the slope is positive. Well, since we've been doing calculus, what that means is everywhere where the first derivative is greater than or equal to 0. Now, I'm going to be honest with you. I kind of disagree with the authors of our textbook right here with this equal then, and the AP Calculus textbook that we use agrees with me. So I'm actually going to be teaching this the way that I was taught with calculus material, and you'll see what I mean in just a moment. And it only differs a little bit, but the good news is that IB recognizes both methods as correct because international, you know what I mean? So we're going to be looking for places where our function has positive first derivatives, because that's where we're going to have positive slopes. That's increasing. And you're decreasing on x values when the slope, or first derivative, is negative, less than 0. So if we look at this picture, which is already graphed for us, and we actually see the coordinates of this local max and the coordinates of this local minimum, it's asking for the intervals where this function is increasing and decreasing. Well, again, what's happening at the maximum, what's happening at the minimum? The reason why they show us those points is because maximums and minimums will always be a place where the first derivative equals 0. Actually, I don't want to use m, I'll use f prime. This is where f prime of x equals 0. This is where f prime of x equals 0. So those are going to be the critical values where things change on this x-axis. So this happened at the x value of -1, and this happened at the x value of +2. So if you were to look everywhere to the left of x equals -1, that's all of this stuff, every tangent line you draw, see if I could draw one like this, or I could draw one like this, or I could draw one like this, every tangent line you draw would have to have a positive slope. Now, everywhere between this x value and this x value, every tangent line that you can draw has a negative slope. So that means everywhere between there, we are decreasing. And again, after this 2, everywhere after that, every single tangent line you could draw would have a positive slope again. So what is the interval of increasing? Well, increasing is going to be from the far left at -infinity all the way up to x equals -1. I'm not going to include -1. I know the IB authors did, but I'm not going to. And it's going to continue increasing again after 2. So from 2 to positive infinity. Now remember, these are x values. They have nothing to do with the y values. I don't care that this thing is going down. This y value doesn't make any difference to us. And again, I don't care that this y value is up here heading towards positive infinity. It does not matter. All that matters is the slopes would be positive to the left of -1. So every x value all the way out to -infinity and after +2. So every x value going up to positive infinity. Therefore, we would be decreasing in between those two intervals from x equals -1 and x equals 2. So now, let me tell you why I disagree with this equal to bar here. Right here at this point at x equals -1, the slope was 0. Is 0 a positive number? Or is 0 a negative number? Or is it both? I would argue that because it's neither positive nor negative, or is both positive and negative, that you can't say you were increasing there. You can't say you were decreasing there. If this thing was just a roller coaster track, and you had the ability to take a picture at any instant you wanted, and say there was a marble going around this, going up and down on this track, and the marble happened to be right here, and you took a picture. If you didn't know what was going on before or after that picture, you would have absolutely no idea if that marble had been traveling up or if that marble had been traveling down. If it had been traveling up or if it had been traveling down. So I would argue that at the point x equals -1, you are not increasing, you are not decreasing. It's the boundary zone between increasing and decreasing, and that's why I'm using the parentheses instead of a bracket. If you were to use brackets here, 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 and here, you'd still be correct in some parts of the world, so therefore IB would accept it. I'm doing what AP Calculus would have expected. Okay? Okay. So now that we understand the idea of increasing and decreasing, we can do it without a graph. See, increasing and decreasing is actually decided by the first derivative. So when it says find the intervals where the functions are increasing or decreasing, without a graph, you're going to have to find the first derivative. So this one here is going to be negative 3x squared by the power rule plus 6x by the power rule. So what do we do here? Well, in this image up here, there was a reason why I showed you that the maximum and the minimum, that your first derivative was equal to 0. That's because these x values, where your first derivative is equal to 0, are known as critical points. So we have to figure out where the critical points are, meaning we have to figure out where the function has a derivative, aka slope, of 0. So we set the first derivative equal to 0, and we figure out where that x is. Well, that's going to involve a lot of factoring for you. So we're going to pull out a negative 3x as a GCF, leaving behind an x minus 2. I can see two places where I'm going to equal 0. That gives me a critical value of x equals 0, because that would make this part out here equal 0, and a critical value at x equals 2, because that would make this part right here equal 0. And we're going to do everybody's favorite, a sign diagram. S-I-G-N, not S-I-N-E. It's not trig, yet. I'm sure a bunch of you cringed when I said yet. There we go. So we have our sign diagram, and all we're going to do is we're going to test values to the left, between, and to the right. So you test a value, and you don't actually do this work. You just do it mentally. Any number to the left of 0, like negative 1. If I put a negative 1 right here, it's going to give me a positive value times a negative value. Now, any number between 0 and 2, like 1. If I plug in a 1 right here, it's going to give me a negative value times a negative value. And if I plug in any number to the right of 2, 3, negative, positive, negative. Mr. M, can I always assume that these signs are going to oscillate between negative and positive? No, you may not. Okay? So it is always a good idea to check. So where are we increasing? We're increasing between 0 and 2. And we're decreasing everywhere else. That means to the left of 0 or to the right of 2, like so. That's it. That's all there is to it. I hope you don't think that's too difficult. Let's pop right along to question B. Same exact process. No surprises here. Find the first derivative. Power rule is going to give us 12x to the third minus 24x squared. We have to set this derivative equal to 0 and figure out where that happens, which is going to require us to factor this thing. I see a GCF of 12x squared, leaving me behind an x minus 2. That gives us critical values of x equals 0, because that'll make the outside 0, and x equals 2. Whoa! The exact same critical values? Will those always be critical values? No. No, it's just a coincidence that the authors chose two questions that have the same critical values, okay? Trust me, if there were any shortcuts or tricks or patterns, I would tell you what they were. Testing intervals. Negative 1. You know what? This number on the outside, it doesn't matter what you plug in, it's always going to be positive, which is cool. So if I plug in a negative 1, I have positive times negative. If I plug in 1, I get positive times negative. See? You see, it doesn't always oscillate. If I plug in 3, positive times positive. So where are we increasing? We're only increasing to the right of 2. Where are we decreasing? Everywhere else except at x equals 0. I am not going to include x equaling 0 as part of my interval. Why, Mr. M? Because at x equals 0, your first derivative is 0. And is 0 positive or is 0 negative? Exactly. So I'm going to say to the left of 0, put together with 0 to 2. If you had included 0, IB would have accepted it. But I'm telling you right now, we never know how they're going to grade, so this will always be accepted. Will including this in the decreasing zone always be accepted? I can't say yes or no, so my strong suggestion is never include the zeros as increasing or decreasing, meaning where the derivative equals 0. It's just a coincidence and it happens to be at x equals 0. And we flip them over to the back. So we have this function, nice rational function. Part A, everybody's favorite, show that. We have been told to show that the slope equals something specific. The derivative equals something specific. And I would like to draw your attention to the fact that this derivative is in factored form. So my strong suggestion is figure out what f of x equals in factored form. The top has no GCF, but the bottom does, it's not on the page, but the bottom does factor to x plus 3 times x minus 1. There. So when we want to find our first derivative, unfortunately, I say unfortunately because it's never fun to do, we're going to have to use the quotient rule. So for part A, which happens to be most of this question, we're going to be using the quotient rule. So u would be 2x minus 3, and v would be x squared plus 2x minus 3, and I'm just going to remind you that it's the same thing as saying x plus 3 times x minus 1. U prime, well, the derivative of any linear is just the number in front of x, so it's just 2. And v prime. See, when I find the derivative of this denominator, I don't want to have to find the derivative when it's factored because that's going to require the product rule. Instead, I'm going to find the derivative like this because this is easier. It gives me 2x plus 2. There. Quite simple. And now we're ready to go ahead and put together our quotient rule. Just let me write it down. U prime v minus uv prime all over v squared. There. Let's put her together. F prime of x equals u prime v, and I'm not going to use the factored format, x squared plus 2x minus 3, minus u v prime, which is 2x plus 2, all over v squared. Now here I am going to use the factored form because it will be much easier to work with. This way I don't have to FOIL a trinomial with a trinomial because this is a product in here. Squaring it literally squares the x plus 3 and squares the x minus 1, which is exactly, whoops, you can't see what I'm pointing at, which is exactly what we have right there. So what we're going to have to do on the top is distribute that to 2x squared plus 2x minus 3. And then minus 6, excuse me, I can multiply. I promise I can. And this is supposed to be a 4. Good gravy. There we go. Minus. Now, I'm going to go ahead and distribute all this. I'm going to FOIL it out. I'm going to assume we all know how to FOIL. It gives me 4x squared plus 4x minus 6x minus 6. Like that. All over. And I'm going to do this. X plus 3 squared, x minus 1 squared. There. So what we're going to have to do here is distribute this negative sign to this entire set of parentheses, this negative 1. And then we're going to have to combine like terms. So I don't know if you guys can hear that alarm going off behind me, but hopefully it shuts up soon. You got to be able to hear that. Anyway, 2x squared plus 4x minus 6 minus 4x squared minus, this is negative 2x, so plus 2x plus 6. All right, I had to pause the video so I could go shut that alarm off. I don't think it was going to stop. Alrighty, so combining like terms, what do we have? Well, negative 6 and positive 6 cancel each other, and these two combine to negative 2x squared And these two make 6x. And all we have to do is factor the top. If you pull out a negative 2x as a GCF, you will have shown that the derivative is exactly what they asked you to show. So factoring the negative 2x out on the top leaves behind an x minus 3 on the inside. And on the bottom, we just have this x plus 3 squared times x minus 1 squared. Would you believe we did all that work for part A? Now part B is actually the quicker part. Part B says find the intervals where it's increasing or decreasing. All right, so we have a fraction here. On the front of these notes, I told you that a critical value is anywhere where the first derivative equals 0. Well, that's only half the story. A critical value is also any place where the derivative is undefined. I mean, how are you going to have a slope at a place where your curve doesn't exist, right? So critical values happen everywhere where the slope is 0 or the slope is undefined. Well, for fractions are only equal to 0 when the top equals 0. So that's going to give us critical values at x equals 0, and that's from this part right here, and x equals positive 3, that's from this part right here. Because if we plug in either one of those numbers, the top turns to 0. Now for the bottom, critical values are any place that make the bottom equal 0 because that's undefined. So x cannot be negative 3, so it's a critical value, and x cannot be positive 1, so it's a critical value. This function has 4 critical values on its sign diagram. So I'm going to push the page up to do part B, and I'm pretty sure the homework will be in frame then. There's the homework for you, and part B. Don't worry, my hand will be out of the way of the homework if it's in the way. Just going to draw a sign diagram with my 4 x values on it. Furthest left to be negative 3. Picture not drawn to scale because who cares? Then 0, 1, and 3. There. We have our sign diagram. Now we just check values. Here's what's cool about this derivative. The bottom is the product of two squares, so the bottom is always positive. So we just have to figure out what the sign on the top is. The sign on the top will basically determine what's going on because the bottom is always positive. So let's plug in a negative 4. It's going to give me a positive number times a negative number. That's negative because, again, the bottom is always positive. Let's plug in a negative 2. It's going to give me a positive number times a negative number. Well, also negative. How about a 0.5? Negative number times negative number. Ooh. How about a 2? Negative number times negative number. And 3. Not 3. What's wrong with me? 4. Number after 3, 4. Negative times positive. Negative. Now technically, because we were undefined at the numbers negative 3 and positive 1, you're supposed to do this for your sign diagram. And this is insinuating that there are vertical asymptotes at those two x values. But when you're writing your answer for increasing and decreasing, it won't make a difference because you're not going to include any of the critical values if you did it the way I asked you to. So we're increasing from 0 to 1, and then again from 1 to 3. And we're decreasing in the other 3 intervals. So to the left of negative 3, between negative 3 and 0, and one more time to the right of positive 3. And that is your lesson on increasing and decreasing functions. I hope you enjoyed it as much as I did. Yay!